Welcome! In this session, we'll explore an interesting coding problem, problem number 990, titled Satisfiability of Equality Equations. Together, we'll break down the problem, discuss its solution approaches, and analyze their efficiency. Let's dive in. In this problem, we are tasked with determining whether a set of equations involving variables can be satisfied. The equations are given as an array of strings, where each string represents either an equality, like A equals B, or an inequality, like A equals B. The variables in these equations are lowercase letters, and they may or may not be distinct. When we encounter an equality equation like A equals B, it means the two variables must represent the same value. Conversely, an inequality equation such as A equals B means the two variables must represent different values. The goal is to return a Boolean value true if it is possible to assign values to all the variables in a way that satisfies every equation, and false if it's not possible. Let's look at an example to understand this better. Suppose the input is an array with two equations, A equals B, B equals A. The first equation, A equals B, tells us that the variables A and B must be equal. However, the second equation, B equals A, states that A and B cannot be equal. These two equations contradict each other, making it impossible to assign values to the variables in a way that satisfies both conditions. Therefore, the output in this case is false. Now consider another example with the input, B equals A equals B. Here, both equations simply assert that A and B are equal, and there is no conflict. Thus, the output is true because we can satisfy both equations simultaneously. Here's another example to illustrate a slightly more complex scenario. If the input is A equals B, B equals C, A equals C, the equations form a chain of equalities, A equals B, B equals C, and therefore, A must also equal C. These equations are consistent with each other, so it is possible to assign values to the variables such that all equations are satisfied. The output for this example is true. Now, consider a different case with the input, A equals B, B equals C, C equals A. The first equation implies that A and B are equal. The third equation implies that C and A are equal, which also means C and B are equal. However, the second equation states that B and C must not be equal, creating a contradiction. As a result, the output is false because it is not possible to satisfy all the equations at the same time. To further understand the problem, let's consider the constraints. The input array can have between 1 and 500 equations. Each equation is a string of exactly 4 characters, where the first and third characters are lowercase letters, and the second and fourth characters define the relationship either equal sign for equality or is not equal to sign for inequality. These constraints ensure that the problem is well defined and that we can focus on solving it efficiently. Now, let's think about some edge cases. For instance, if the array contains only one equation, like A equals A or A equals B, it can always be satisfied since there are no conflicting conditions. On the other hand, a self-contradictory equation like A equals A immediately results in false because a variable cannot be both equal to and not equal to itself. Finally, let's explore two additional scenarios. First, if the equations involve completely disconnected sets of variables, such as A equals B, C equals D, each set can be satisfied independently, so the entire array of equations can be satisfied. Second, when the input size is large, up to the maximum of 500 equations, it's crucial to have an efficient algorithm that can handle cases where all variables are interconnected through chains of equalities. The solution must process such scenarios without exceeding time limits, ensuring scalability and correctness even for the largest inputs. To solve the satisfiability of equality equations problem, we considered 3 main approaches. The first is the brute force approach, which involves directly assigning arbitrary values to variables and checking if the given constraints are satisfied. For equations with equal sign, we assign the same value to both variables, while 4 is not equal to sign equations, we ensure distinct values. Although this method is simple to implement, it comes with a major drawback: the time complexity grows exponentially with the number of variables, making it computationally infeasible for large input sizes. Next, the graph-based approach leverages the idea of connectivity. Here, we treat variables as nodes in a graph and use equal sign equations as edges to connect them. If two variables can be connected through these equal sign edges, they belong to the same connected component. For is not equal to sign equations, we check that the two variables are not in the same component. This introduces an efficient way to model the problem using graph traversal techniques such as DFS or BFS to identify connected components. Together, these approaches establish a foundation for understanding the solution space, but they also highlight potential limitations in scalability and efficiency. Now, while the graph-based approach efficiently models the problem and avoids the brute force method's exponential complexity, it still requires explicitly traversing the graph multiple times. This can introduce overhead, especially as the number of variables and equations grows. The graph-based approach typically has a time complexity of O, n plus k, where n is the number of variables and k is the number of equations, and a space complexity of O, n plus k, to store the adjacency list in visited set. While this is much better than brute force, it may still feel cumbersome, especially when compared to more refined techniques. To address these concerns, the third and final approach we consider is the union find method, also known as disjoint set union. This approach is optimal because it is specifically designed for handling equivalence relations. Here, each variable is treated as part of a set representing equivalency. Using union operations, we can group variables connected by equal sign equations into the same set, and with find operations, we can efficiently verify that variables in is not equal to sign equations belong to different sets. This method simplifies both the modeling and the solution process, making it highly effective for this problem. Union find builds on the strengths of the graph-based approach while eliminating its inefficiencies. By using the union find data structure, we can efficiently perform both union operations, to group variables, and find operations, to check the relationships between them. This makes it an excellent fit for solving equivalence problems like this one. The time complexity of this approach is O, n plus k asterisk alpha, n, where alpha represents the inverse Ackermann function, which grows extremely slowly and is nearly constant for all practical purposes. The space complexity is O, n, as we only need to maintain the parent and rank arrays. This means that union find is not only faster but also more memory efficient compared to the graph-based strategy. Its ability to elegantly handle both equal sign and is not equal to sign equations makes it the most scalable and robust solution for this problem. By leveraging this data structure, we can confidently address the problem's constraints while minimizing computational overhead. This efficiency and simplicity are key reasons why union find becomes the ideal choice for this problem. In comparing the three approaches, it's evident that union find stands out as the optimal solution. The brute force approach, while conceptually straightforward, is completely impractical due to its exponential time complexity. The graph-based approach is a significant improvement, offering a more structured way to model the problem, but it still requires managing adjacency lists and explicit graph traversal, which can become cumbersome. On the other hand, union find offers the best combination of speed and simplicity. With its near-constant time operations and minimal space requirements, it excels in handling even large-scale test cases. This makes it a favorite among competitive programmers and a natural fit for problems involving equivalence relations. Ultimately, union find aligns perfectly with the core requirements of the satisfiability of equality equations problem, striking an ideal balance between efficiency, clarity, and scalability, and making it the clear choice for our solution strategy. To solve this problem, we need to evaluate whether a series of equality and inequality constraints between variables can be satisfied simultaneously. These constraints are given as equations like A equals B or A equals B. The challenge lies in determining if these relationships can coexist without contradiction. For example, if we have A equals B and B equals C, we must check whether these constraints are logically consistent. The approach we use is based on the union find data structure, which is also known as disjoint set union. The intuition is to treat variables as nodes in a graph and use union find to group variables that are equal. Once these groups are formed, we can then check if any inequality constraint violates the structure of these groups. This method is efficient and leverages the power of graph-based algorithms to solve the problem systematically. The first step in the algorithm is to initialize the union find data structure. Here, we create a parent array, where each element represents a node, and initially, every node is its own parent. This means parent, I, equals I for all nodes. This setup ensures that each node starts as its own independent set. Additionally, we use a rank array to optimize union operations. The rank helps us keep the tree structure flat by always attaching the smaller tree to the root of the larger tree. Once initialized, we process all equality constraints first. For each a equals b constraint, we find the root of both a and b using the find function, which employs path compression to optimize performance. If the roots are different, we unify the two sets using the union function. This groups all variables that are equal into the same connected component. After grouping variables based on equality constraints, the next step is to check for conflicts in the inequality constraints. For each a equals b constraint, we again use the find function to determine the root of both a and b. If the roots of these two variables are the same, it indicates a conflict because a and b are in the same group, which violates the inequality constraint. On the other hand, if the roots are different, the inequality is satisfied, and we can safely continue checking the remaining constraints. At the end of this process, if no conflicts are found, it means all constraints can be satisfied, and we return true. However, if a conflict is detected at any point during the inequality check, we immediately return false, as the constraints are unsatisfiable. The algorithm's efficiency is largely due to key optimizations in the union find data structure. Path compression ensures that during find operations, every node directly points to the root of its set. This reduces the time complexity of subsequent find calls. Union by rank further optimizes the structure by always attaching the smaller tree under the larger tree during union operations. Together, these optimizations make union find operations extremely efficient, with a time complexity of O, alpha, n, where alpha, n, is the inverse Ackermann function, which grows very slowly and is almost constant for practical input sizes. Additionally, the algorithm separates concerns by processing equality constraints first, forming connected components for variables that are equal. This ensures that we can later verify inequality constraints efficiently. The ability to detect conflicts using representative roots ensures the correctness of the algorithm, as we can quickly identify and resolve any contradictions. To implement this algorithm, we rely on two key data structures. The first is the parent array, which tracks the parent node for each variable. This array represents the forest structure of the union find. Initially, every node is its own parent, and as unions are performed, the parent array reflects the connected components of the graph. The second data structure is the rank array, which helps optimize the union operation by keeping the tree as flat as possible. Both arrays require O, n, space, where n is the number of variables. In terms of complexity, the time complexity of the algorithm is O, n asterisk alpha, n, where n is the number of constraints, and alpha, n, is the inverse Ackermann function. The space complexity is O, n, due to the storage of the parent and rank arrays. These complexities make the algorithm highly efficient for large inputs. When applying this algorithm, it's crucial to handle certain edge cases carefully. For example, constraints like a equals b, b equals c, and a equals c inherently conflict, and the algorithm must correctly identify such cases as unsatisfiable. Additionally, we must account for disconnected variables, those that do not appear in any constraints, and ensure they do not affect the result. Single variable constraints, such as a equals a or a equals a, are edge cases as well. The first is always true since a variable is inherently equal to itself, while the second is always false because a variable cannot be unequal to itself. Finally, if there are no constraints at all, the result is trivially true since there is nothing to satisfy. Properly handling these edge cases ensures the robustness of the solution in all scenarios. Here, we start by defining a class called solution, which contains the main function equations possible. This function will determine whether the given equations can be satisfied. We begin by defining a helper function called find, which is used to determine the root or representative of a given variable. If the variable is not its own parent, we recursively update its parent using path compression, which helps optimize future lookups. Next, we define another helper function, union, to unify the sets of two variables. It first finds the roots of both variables and, if they are different, connects one root to the other. Then, we initialize a parent dictionary for all 26 lowercase English letters, with each variable initially being its own parent. After that, we process all equations that involve equality, denoted by equal sign. For these equations, we call the union function to ensure that the variables on both sides of the equality belong to the same set. Next, we handle the equations involving inequality, denoted by is not equal to sign. For each of these equations, we check whether the two variables being compared have the same root using the find function. If they do, it means there's a contradiction because two variables that are supposed to be unequal are found in the same set, so we return false. If no contradictions are found after processing all equations, we return true, indicating that the equations can be satisfied. This approach efficiently handles the problem by leveraging the union find data structure with path compression, ensuring that both the equality and inequality constraints are evaluated correctly. Here, we start by importing the required packages and defining our solution class. The main method we are working with is equationsPossible, which determines if a given set of equations can be satisfied. To solve this, we use the union find data structure, which helps us efficiently manage connected components. We initialize a parent array of size 26, representing the 26 lowercase English letters, and set each letter to be its own parent initially. This essentially means that each variable starts out in its own separate set. Next, we define a helper function, find, which retrieves the root of a variable. This function includes path compression to optimize the union find operations, ensuring that every node directly points to its root for faster lookups in future operations. Lastly, we define a union helper function, which merges the sets of two variables by updating the parent of one set to point to the root of the other. This operation ensures that the two variables belong to the same connected component. Now, we process the equations provided in the input. First, we handle all the equal sign equations, as these indicate equality constraints. For each equation, we calculate the indices of the two variables by subtracting it from their ASCII values, and then unify their sets using the union function. This step ensures that all variables appearing in equality relationships are grouped into the same connected component. Next, we process the is not equal to sign equations, which represent inequality constraints. For each inequality, we again calculate the indices of the two variables and check if they belong to the same set using the find function. If they do, it means there is a contradiction, as two variables that are supposed to be unequal are in the same connected component. In this case, we return false. If no contradictions are found after processing all the equations, we return true, indicating that the equations are satisfiable. This approach ensures we handle both equality and inequality constraints efficiently using the union find algorithm. To solve this problem, we use a union find data structure to manage the relationships between variables. First, we initialize a parent dictionary where each letter from A to Z is its own parent. This means that initially, all variables are in their own separate sets. Next, we process the first equation, A equals B. This equation tells us that A and B belong to the same set. To achieve this, we perform a union operation. We start by finding the root of A, which is simply A itself, and the root of B, which is B. Since their roots are different, we unify their sets by setting the parent of A to B. Now, the parent dictionary reflects that A and B are in the same set. Moving on to the second equation, B equals A, we need to check if B and A belong to different sets. We find the root of B, which is B, and the root of A, which, through path compression, is also B. Since both variables share the same root, the equation B equals A is contradictory because B and A cannot belong to the same set. Therefore, we return false in this case. Now let's examine a second example with the input, A equals B, B equals C, A equals C. We start by initializing the parent dictionary, where each variable is its own parent. The first equation is A equals B. Again, we find the roots of A and B, which are A and B, respectively. Since the roots are different, we perform a union operation by setting the parent of A to B. Next, we process the equation B equals C. We find the roots of B and C, which are B and C. Since these roots are also different, we unify the sets by setting the parent of B to C. At this point, the parent dictionary reflects that A, B, and C are part of the same connected set. This setup ensures that all equalities between these variables are satisfied. For the final equation in this example, A equals C, we need to verify if A and C belong to the same set. Finding the root of A involves traversing through its parent chain, A points to B, and B points to C, so the root of A is C. Similarly, the root of C is directly C. Since both variables share the same root, the equation A equals C holds true. Therefore, the entire set of equations is consistent, and we return true. Shifting to another example, consider the input, A equals B, B equals C equals A. As always, we initialize the parent dictionary with each variable pointing to itself. The first equation is A equals B, so we perform a union operation by setting the parent of A to B. This unifies A and B into the same set. Next, we evaluate the equation B equals C. To check if this inequality holds, we find the roots of B and C. The root of B is B, and the root of C is C. Since the roots are different, the inequality B equals C is satisfied, and we can continue processing. Finally, we process the equation C equals A. To unify C and A, we first find their roots. The root of C is C, and the root of A is determined through its parent chain, A points to B, so the root of A is B. We then perform a union operation by setting the parent of C to B, effectively adding C to the same set as A and B. After this union, we recheck the earlier inequality B equals C. Finding the root of B gives B, and finding the root of C now also leads to B, indicating that B and C are in the same set. This violates the inequality B equals C, making the equations contradictory. Thus, we return false for this example. The time complexity of our solution is determined by analyzing the main operations within the equation's possible function. First, we initialize at parent dictionary for all 26 lowercase letters. This operation is constant because it involves a fixed number of elements, so it takes 26 time, which simplifies to 1. Next, we process the equations of the form A equals B. For each of these equations, we perform a union operation, which itself consists of two find operations. The time complexity of a single find operation is alpha n, where alpha n is the inverse Ackermann function, a very small constant for practical purposes. If there are k such equations, this step requires k asterisk alpha n time in total. These two components form the foundation of our time complexity analysis. Now, when processing the equations of the form A equals B, we need to perform two find operations to confirm whether the roots of A and B are the same. Since there are at most n total equations, the number of equals equations is n(k), where k is the number of equals equations. Each find operation in this step also has a complexity of alpha n, so the time required is and k asterisk alpha n. When we combine all the steps, the total time complexity becomes 1 for initialization, k asterisk alpha n for processing equals equations, and k asterisk alpha n for processing equals equations. This simplifies to n asterisk alpha n, which is effectively n for practical purposes, since alpha n grows extremely slowly. For space complexity, the main contributors are the parent dictionary and the recursive stack used in the find function. The parent dictionary stores the parent for each of the 26 lowercase letters, which requires 26 space. Since this is a fixed number, it simplifies to 1. In the find function, the recursion depth is proportional to the height of the tree. However, with path compression, the height is effectively reduced to alpha n, which is negligible for practical inputs. Combining these factors, the total space complexity is 1, as the dictionary size is constant and the recursion depth is minimal. Looking at the best, average, and worst case scenarios, in the best case, all variables are already unified, meaning each find and union operation takes minimal time, resulting in a time complexity of n. In the average case, some variables are unified, and path compression reduces the tree height, so the time complexity remains n. Even in the worst case, where the equations form a long chain of dependencies and path compression is applied repeatedly, the time complexity is still n. Comparing this with a brute force approach, which would involve checking all possible combinations of variables to identify contradictions, we see a significant improvement. Brute force could result in a time complexity of n squared, or worse, while the union find algorithm achieves n asterisk alpha n, which is effectively linear for practical inputs. The time complexity of the union find algorithm is primarily driven by the find operation with path compression. The amortized time complexity of find is O, alpha, n, where alpha, n, is the inverse Ackermann function, which grows extremely slowly. Since the algorithm performs at most n find and union operations, the total time complexity is O, n asterisk alpha, n. For all practical purposes, this simplifies to O, n, as alpha, n, is nearly constant for any reasonable input size. This mathematical property ensures the efficiency and scalability of the solution when handling large numbers of equations. When solving algorithmic problems, it's important to be mindful of common pitfalls that can trip you up. One major issue is overlooking edge cases. For instance, problems involving arrays require careful handling of scenarios like empty arrays, arrays with only one element, or even cases involving negative numbers. Forgetting these can lead to subtle bugs or incorrect results. Another frequent mistake is sticking to brute force solutions without considering their inefficiency on larger inputs. While brute force might work for small test cases, it often fails due to time limits in competitive programming settings. Similarly, ignoring problem constraints such as assuming inputs are always valid can result in runtime errors like division by zero or accessing elements outside an array's bounds. It's also common to overcomplicate solutions by using advanced techniques when simpler ones, like sorting or prefix sums, would suffice. This not only increases debugging time but also makes your code harder to understand. Lastly, while optimizing for time complexity is crucial, don't overlook space complexity. Using excessive memory, like creating unnecessary auxiliary arrays, can make your solution impractical for larger datasets. Now let's discuss some valuable insights for interviews. Recognizing patterns is a game changer. Many problems are just variations of common paradigms like sliding windows, dynamic programming, or divide and conquer. Identifying these early can save you significant time. Additionally, consider the trade-offs between time and space complexity. Interviewers often ask you to improve one at the expense of the other, so being able to weigh these factors is essential. Another key tip is to clearly explain your thought process. Even if you don't arrive at the optimal solution, demonstrating logical reasoning can earn you partial credit and showcase your problem-solving approach. Testing your solution is equally important. Verbalize how you'd handle edge cases and walk through your code to highlight your debugging skills. Finally, tackle problems modularly by breaking them into smaller subproblems. This not only simplifies your thought process but also keeps your code organized and easier to maintain. To strengthen your understanding, it's helpful to explore related problems. For example, 2-sum is a classic problem that emphasizes the use of hash maps for efficient solutions. Building on that, 3-sum introduces additional complexity where sorting and the two-pointer technique become invaluable. Another great example is longest substring without repeating characters, a textbook sliding window problem that tests your ability to manage dynamic ranges. Similarly, subarray sum equals k showcases how prefix sums and hash maps can be combined to solve problems efficiently. As you approach these problems, it's good to be aware of alternative strategies. Brute force methods are simple and intuitive but should generally be used for validating small test cases due to their inefficiency. Optimized approaches, like hash maps or two-pointer techniques, strike a balance between time and space complexity and are suitable for most scenarios, though they require careful handling of edge cases. Divide and conquer is another powerful approach, especially for problems like finding the maximum subarray, but its implementation can be more complex. Lastly, dynamic programming is excellent for problems with overlapping subproblems, though it can demand higher space usage unless optimized with methods like memoization or tabulation. Thanks for following along. We've summarized the key points of the solution and its efficiency. Remember, mastering these techniques will boost your problem-solving skills. Don't forget to practice similar problems and stay tuned for more tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!